Good day, everyone. My name is Knowledge, and I appreciate you all for being here. I like to think that there's a parallel universe out there where I'm actually a teacher. So welcome to maths class. And now that you're all here, there's no getting out. Mathematics has been dubbed the language of the universe. In fact, it was Galileo, one of the greatest astronomers and philosophers of his time, who described mathematics as the language with which God created the universe. However, this language still remains a very daunting subject for most people. This is partly because after many years of being forced to learn mathematics in the school system, most people still struggle to find the relevance of the subject in their day-to-day lives. So, not only is maths this thing that was forced onto us, but it also seems, for the most part, that it's the not so useful bits of it that gave us a tough time throughout all those years. I mean, how much of all the maths you have had to learn in your life do you actually get to make use of today? Not to bring back the traumatic experiences of the past, but I'm pretty sure that most of us have gone through this or a similar kind of agonizing experience with maths. Back in my university years, I did a course called Signals and Systems, and I had heard lecturers refer to this course as the heart of electrical and information engineering. Amongst the students, however, the course was known by a different name. It was called the gatekeeper to graduation, because it was the one course that kept most people from graduating in record time. And it was in this course where I first learned about the concept of Fourier analysis as applied to different types of signals. And as with all maths that seems to lack relevance in our lives, I learned the bare minimum that was necessary for me to pass the course. As for the life of me, I just couldn't get what the whole thing was all about. A few years later, I was still not satisfied with the idea of having left with just a bare minimum understanding of the course. So I turned to programming for help. I find programming to be a really powerful tool because it allows us to translate abstract ideas and concepts into something concrete that we can interact with. And it also transforms the process of exploring these ideas into a fun endeavor. It is one way of giving relevance to the seemingly abstract concepts that just don't seem relevant enough for us to want to spend our time trying to understand. So I decided to make use of Fourier analysis to develop a program that draws 2D images. I'm going to be visually explaining this concept of Fourier analysis as well as demonstrating its applications in 2D drawings through this Java program that I wrote, inspired by the incredible work of sketch artists. It is my hope that through this presentation, I'll be able to take away some of that fear of mathematics, get you to fall in love with it, and get you curious enough to want to play around with it. There is a quote by Robin Williams, which I first heard in an artificial intelligence course by one of the best teachers I've ever had the pleasure of listening to, the late Professor Patrick Winston of MIT. He said, once you name something, you are conscious of it. You have power over it. You are in control. You own it. What that meant to me is that the first step in really understanding something is knowing the meaning to and understanding the words that are used to describe it. But more important than the name is the concept behind the name. And that's what we should be focusing on when we really want to understand something. The key point that I'm trying to make here is that the names we give to concepts are oftentimes scarier than the concepts they describe. And mathematics is rife with such complex named concepts that scare people away and have them not wanting to engage with it. And this does not just apply to the names we give to mathematical concepts, but to the mathematical equations, symbols, and expressions that most mathematical texts are full of. On some random day, I decided to search for the word mathematics on the internet. I opened the image results, and This is what I was presented with. To be honest with you, all these symbols, equations, and expressions don't exactly scream welcome to mathematics. Similar to names, people look at these equations, symbols, and expressions, and they immediately think that because they don't understand what each of the symbols, equations, and expressions mean, then it's probably something that is too complicated for them to understand. And such couldn't be further from the truth. Let's take the equation x squared plus y squared equal to 2, for example. Now, if you were to go around asking people what this equation described, chances are most people will probably have a hard time explaining exactly what this equation described. And yet, this equation happens to describe one of the most common shapes in the world, which is a circle. A shape formed by joining points that are the same distance from some central position. A simple concept to understand. Now, if you were to go around asking people what this shape was, I'm pretty sure that most people will be able to say that it's a circle. Or at least I hope they would. So, I'm going to try as much as possible to get you to see beyond the names, see beyond the symbols, equations, and expressions, and focus on understanding the concept. Fourier analysis already sounds like a complicated concept because, number one, it has the word Fourier in it, which few, if any amongst us here, can actually say what it means. And number two, it has the word analysis in it, which already plants into our minds this idea that a detailed examination is required. And number three, it's related to mathematics somehow. So that is already scary. Allow me to take away that fear by telling you that Fourier analysis is the analysis of complex waveforms expressed as a sum of trigonometric functions, the frequencies of which form a harmonic series. Well, maybe some of you got what Fourier analysis actually means after listening to that. But I'm pretty sure that most people still don't get what Fourier analysis actually means after listening to that definition. And unfortunately, this is one of the definitions that you will come across on the internet if you were to search for what Fourier analysis actually means. But enough about that. I want you to think happy thoughts. I want you to think about a smoothie. This beverage that is made up of a variety of ingredients like fruits, vegetables, maybe some milk, yogurt, and the like. These ingredients are pureed until you get a smooth concoction that is totally different from the original ingredients that were used to make it. But even though the smoothie is now a totally different product from the original ingredients that were blended together, we still know that it's a sum of all those ingredients that were blended together. Suppose somebody came and gave you a smoothie, but you didn't know the ingredients that were used to make that smoothie, and you wanted to make more of the exact same smoothie for yourself. How would you go about doing so? Well, if you had some sort of a machine that could take the smoothie that you have and then identify the ingredients and quantity of each ingredient, you could use that machine to get the recipe for the smoothie you have and then use that recipe to make more of the exact same smoothie. By now you're probably wondering, what does a smoothie have to do with Fourier analysis? Well, it all begins with this round peg in a square hole by the name of Joseph Fourier, who proposes this crazy idea that any function, no matter how complicated, can be synthesized just by adding some trigonometric functions together. In essence, what he was saying is that any general function that you can think of is made up of these smooth wave-like sinusoidal components, which we call trigonometric functions. Now, this idea was met with a lot of skepticism, even from well-respected mathematicians like Lagrange and Laplace. And who could blame them? Because who could, at the time, believe that these smooth sinusoidal components can be added together to form all kinds of functions with all kinds of bends and edges. Well, fast forward to today, this idea has a whole field of mathematics built around it, with a wide range of applications from image and pattern recognition to quantum physics and to stock markets. If you think of these general functions as smoothies, and you think of the simpler trigonometric functions as the ingredients that the smoothies are made of, then Fourier analysis is all about building this mathematical and smoothing machine that can take any general function and give you the right combination of trigonometric functions that can be added together to reconstruct that function. Now, I'm pretty sure that you probably noticed that there was nothing complicated enough to explain the word Fourier in that definition. And you were right to notice that, because Fourier is just the name of a person, and therefore has nothing to do with the actual concept that we want to talk about. The word analysis comes from the fact that this is something that people have studied and continue to study, to find different ways of representing general functions as a sum of trigonometric functions. And mathematics, well, that's just an area of knowledge, and it has nothing to do with how simple or complicated a concept within that area of knowledge is going to be. So now that we have broken down the name Fourier analysis, and we also know the concept behind the name, we are conscious of it, we have power over it, we are in control, we own it, and we are now ready to build our own mathematical and smoothing machine. Fourier analysis tells us that the two ingredients that all general functions are made of are the sine function and the cosine function. The equation you see in green is the algebraic equation for a sine function, and the equation you see in orange is the algebraic equation for a cosine function. What we see below the algebraic equations are the sine graph and the cosine graph. So thinking of an image as some general function, we are going to use Fourier analysis to decompose that image into its sine and cosine components, and then have the computer reconstruct the original image from the sine and cosine components that it calculated, which is kind of what a sketch artist can be thought to be doing, looking at something physical and replicating that on a piece of paper or a canvas. Algebraic expressions, however compact, are usually scary and unintuitive to understand. This is an example of what an algebraic sum of trigonometric functions looks like. And most of our traumatic experiences with maths come from expressions like this that take away the beauty in mathematical ideas and immediately take us back to that one day when we had to use 2 answer sheets to solve a single math problem. But today is not that day, because we are not going to be solving math problems like this. So please do stick around. Let's rather shift our attention to graphical representations and their sums instead. This is what the sum of the 3 trigonometric functions look like when each trigonometric function is represented as just a graph. And the purple graph is what their graphical sum looks like. We notice that in places where all the 3 individual graphs are positive, we get a spike in our sum graph. It's more positive. And in places where either of the 3 individual graphs is negative, we get a slight dip in our sum graph. That is because the negative graph takes from the positive sum of the other 2. And in places where all the 3 individual graphs are negative, our sum graph is also negative. So visually, the sum of trigonometric functions makes sense. And it just took one graph paper and some pretty colors to do so. What we have seen from all of this is that looking at something from a different perspective can sometimes give us a better insight into it. It can help us analyze it differently and potentially understand it better. So I want us to look at trigonometric functions from a third perspective before we actually get down to applying Fourier analysis to draw some images. Let's think about a line which starts at the point x equal to 0, y is equal to 0, and ends at the point x is equal to the cosine of 45 degrees, y is equal to the sine of 45 degrees. This line makes an angle of 45 degrees with the positive x-axis. And I must tell you now that there's nothing significant about this angle being 45 degrees. We call the point x equal to 0, y equal to 0, the origin, because that is where we start. And we call the point x is equal to cos of 45 degrees, y is equal to the sine of 45 degrees, the terminal point, because that is where we end. So let us also give a name to this line. I think vector sounds fancy and exotic enough, so we will call this line a vector. We can decide to get this vector to rotate by changing the angle that it makes with the positive x-axis from being the constant 45 degrees to a variable or a quantity whose value changes. When we do that, we get a rotating vector like this one, which we call a phasor. That is just to differentiate it from the static vector that we saw previously. Now, if we trace the path made by the terminal point of the phasor as it rotates, we obviously get a circular path like this one. And if we attach some horizontal cursor to the terminal point of the phasor as it rotates, we notice that the horizontal cursor just moves up and down. So let's say we decide to plot the y values of the terminal point of the horizontal cursor as it rotates. What we notice is that it actually traces a sine function, which is one of the ingredients that all general functions are made up of. I don't know about you all, but I think this is really cool. And what it's telling us is that if you walk around a circular path, then your position over time actually traces a sine function or a cosine function, depending on how you look at it. So instead of thinking about general functions as being made up of trigonometric functions, we can think about them as being made of circular paths like this one. What we are seeing here is the sum of the three previous trigonometric functions that we had earlier on, when each of the trigonometric functions is viewed as a circular path. And we notice that the size and speed of rotation of each circle are different. And these depend on the amplitude and frequency of the original trigonometric function that they each represent. And to get the sum of trigonometric functions using circular paths like this, we arrange them such that the center point of each subsequent circular path is at the terminal point of the previous circular path's rotating phasor. And when we have circular paths arranged in this way, they are called epicycles. So this is an epicycle sum of trigonometric functions. With that understanding in mind, let us get back to this idea of our mathematical machine that can decompose functions into their sine and cosine components, or epicycle components. It turns out that mathematicians have already discovered an equation for this machine, and they called it the Fourier transform. This is what the equation of the Fourier transform looks like. But we're not going to be working with this specific equation today. Instead, we'll be working with a variant of the Fourier transform equation called the discrete Fourier transform. And this is what the equation of the discrete Fourier transform looks like. I'm sure that for most of you, this equation probably looks more complicated than the previous Fourier transform equation that we just saw. But I can assure you that this version of the Fourier transform is actually way easier to understand and to translate into code. All that we have to do is understand the meaning of each symbol, variable, and subscript that makes up this equation. The symbol that looks like the weird capital letter E is called the summation symbol. And whenever you see the summation symbol, you must immediately know that you are going to have to implement some kind of a loop in your code. The equation n equal to 0 below the summation symbol indicates our summation starting point. So that is the point at which we are going to start our loop iteration. And the expression capital N minus 1 above the summation symbol is going to form the summation endpoint. And that defines the point at which we stop our loop iteration. The expression to the right of the summation symbol is what's going to make up the body of our loop. Small letter x is the input that we give to our Fourier transform machine. So in our case, that is going to be some list of image points. And capital letter X is what we're going to get back from our Fourier transform machine. So in our case, it's going to be either a list of phasors, a list of epicycles, or a list of trigonometric functions, because either of these can be used to reconstruct the original function that we give to the Fourier transform machine. Subscript n just indicates the nth item in our input function, so it's going to be the nth image point. And subscript k means the kth item in our list that's coming out of the Fourier transform machine. So it's going to be the kth epicycle or the kth phasor. The variable I just indicates an imaginary component, but that is going to be irrelevant in our implementation. So you can just think of it as something to ignore. And now, with that whole understanding in mind, I feel we can now open up our IDE and see what the implementation of this equation looks like when it's translated to some Java code. Well, we're not really going to open an IDE because we have the code over here. This function is what my implementation of the discrete Fourier transform looks like. It takes in a list of coordinates, which I read off an image. So this list of image coordinates is what makes up our input function. And the first thing that I do is convert each of the image coordinates to a phasor or a rotating vector. But I set the frequency of rotation for each phasor to 0, which basically just makes it a static vector. And the reason I do this is because I want to perform some vector arithmetic, which is more intuitive than, say, epicycle arithmetic. I don't know how to do that. And then the next thing that I do is I initialize the output list to also be a list of phasors. And I initialize it to be a list of phasors instead of epicycles for the same reasons. It's easier to perform phasor or vector arithmetic than it is to do epicycle arithmetic. But we know that once we have a list of phasors, we can simply get our list of epicycle components by tracing the terminal point of each phasor as it rotates. So that makes up our input, our output. We also initialize our variable n to just be the size of the input signal that we give to our mathematical Fourier transform machine. And once we have done all of that, we get to our loop, which is actually the heart of the Fourier transform itself. We notice here that we actually have a nested for loop instead of like just a single for loop. The reason being that to get a single phasor component or to get a single epicycle component, we actually need to sum through all of our image points to do so. Hence the reason why we have a nested for loop like this. In our for loop, the first thing that I do is initialize this variable called sum. And it's also just another phasor that we are going to be accumulating all of our results from the inner for loop to get the kth phasor component. Once we have done that, we get into our inner loop. And then in the inner loop, the first thing that I do is notice from the discrete Fourier transform that we are simply multiplying the nth image point by some difference of the cosine and sine of some common angle. So I take that and put it into a variable called theta. Once we have that variable, the next thing we do is create another phasor object called multiplier. And this just represents that difference of the cosine and sine that we are going to be multiplying our nth image point by. After doing that, we get to line 49, which is actually what our sum expression was. We take an nth image point, we multiply it by this difference of the cosine and sine function, and then we just add all those together to get the kth phasor component. That's what comes out at line 51. You will notice that at line 51, we are also differentiating the x-coordinate of the terminal point of the phasor and the y-coordinate of the terminal point of the phasor by n, that is the number of image points that we have. And the reason for that, well, it's actually beyond the scope of this presentation. But what I want you to know from that is that it allows us to get the exact size image as we put in, rather than some largely scaled version of it. And once we are done with all that, we just add the kth phasor component to our output list. And the last thing that I do, which has nothing to do with the Fourier transform equation itself, but just makes sure that our animation is going to be something that looks nice, is to sort all the phasor components that we have by magnitude. And this ensures that biggest epicycles are going to be generated first. Once we have all of this, the discrete Fourier transform translated into code, we can then run our program that applies this very same function and see what the result of it looks like. Obviously, there are more components to the program than just the discrete Fourier transform itself, but this is the heart of what the program is going to be doing. So just allow me a bit of time as I switch to the IDE this time, and then I will show you what the program actually looks like. Okay. Any time now. Okay, there we go. And this is our program. Please forgive the not so nice UI, UX design on this thing, but it does the job, so we are fine. So this is the program that I wrote, and it applies the concept of the Fourier transform to draw some images. I have some preloaded images here that you can just select, and then you watch it as it first breaks it up into its sine and cosine components, generates these epicycle components out of that, and then it animates the whole process of reconstructing that image. So the first one that I'm gonna use here is, I think this one is cute, so we're gonna go with that one. And the first thing that it does is it shows you the arrangement of all the epicycles that it calculated, which when it sums up all of them together are gonna give us the image that we gave it. So when we click the play button here, we see the process of actually reconstructing one of the preloaded images that we have. So what I did with these preloaded images is, because when you read an image, you're probably gonna read it either in row major form or column major form. But in doing it like that, if you plot all those points in the order in which you read them, you don't exactly get back the exact same image as you put in. So the first thing that I had to do is arrange all these images in that order that they are actually gonna trace the image that we have. And that's what our preloaded images actually are. And our program can draw something like this, which I think is really beautiful. And Besides the preloaded images that we have, we are also able to draw an image from disk, which definitely has to be the BBD logo. And we can do something like that. It takes a bit of time to do its calculations, but then it's complete now, and we click play, and we see it reconstruct the BBD logo. When I actually implemented this program the first time, I spent quite a bit of time just watching it draw all of these images. And I wanted it to draw myself so bad that I actually uploaded a picture of myself. And it did draw it, don't get me wrong, but it took a bit of time, which for this demo is not what we have. So yes, the BBD logo it is. And we are done. So the last image that I want to draw, which also concludes this whole presentation, is one that I very like so much. And let's see what it's going to do. So when I first got this program to draw images like this, I was super excited. I wanted to share it with everyone. And it's that excitement that got me to sign up for Escape. A few weeks of preparations down the line, that's when the reality hit me that I'm actually trying to give a 45-minute talk about maths. And the idea just got crazier and crazier with time. And I don't know how many times I actually thought about quitting the whole thing. But I'm glad I didn't. So it is my hope that after listening and watching all of this, you have developed some liking of mathematics and some curiosity of it, at least enough to earn it a date. I hope that when you leave this place, you won't be scared to explore ideas and concepts out there simply because they sound too complicated. Take time to understand the meaning of the words that are used to describe the concepts. Try to understand the concept from a different perspective, and maybe even give it some relevance in your life, probably by writing some code. But whatever it is that you do, keep learning and don't settle. Thank you. Yes, questions? Okay.
All right, so I'm Omar, and just a quick question. So for all of these demos, it's kind of been a monocolor outline of the image. Are the source images also outlines, or is it doing some kind of edge detection?
So what I did with all the images that I drew here today, I first actually did some pre-processing on them. I used this other online tool to just make them black and white. I forgot the name of it, but I can find it if anybody is interested. So the reason I did that is not because it can't draw an actual color image, but it was because of the processing time that I wanted to sort of like shorten down, right? So it can draw an actual color image, but it's going to take a while. To prevent that, I had to remove the background, sort of like get the outline of the image to have like this black and white picture that is quicker to draw.
Oh, okay, cool. That makes a lot of sense. And then one last question. Is there anywhere where we can download this program and maybe run it ourselves?
Yes, it's on a GitHub repo, which I guess, I don't know how it's going to be made available to everyone, but if you want, I can also give you access to that. It's a public repo anyways. So yeah.
All right, I'll come find you later. Thanks.
Sure.
Hi, I'm Tori. I was actually going to ask the exact same question, but I have another one.
Yes.
Can you set the resolution of these images, or like the number of circles, or that nth number? Or is it something that gets calculated?
So you can, because the number of circles that actually comes out of that is equal to the number of pixel coordinates that it reads off an image. And then what I do, again, to just make it faster, I actually did bring down the resolution of these images, sort of like I skip every fourth pixel coordinate because I felt it was still enough to get the actual image that we want. I mean, obviously, a better thing would be, I think, probably to have it as part of the UI to set that resolution if you're going to have the time to wait for it to draw a proper image. But yeah, it's something that you can do.
It's a really cool program.
Thank you.
Okay, Robert Jones. I wanted to know, are you aware of a way to do a simplification as opposed to just using the image size as your number of vectors that are rotating? Can you actually process the image and compress the number of rotating vectors?
So I don't think I quite get the question.
Is there a way to do some sort of optimization on the vectors that represent the image? Because you said that the way you got there is by the size of the image, which is why you were compressing.
Yes.
Just by skipping every fourth pixel. Is there a more intelligent compression algorithm out there?
I believe the fast Fourier transform is one of those. It can actually make it quicker to get to the results that you want. But yeah, I felt this particular implementation of the discrete Fourier transform itself was way easier to implement, even though it's slower. So yeah.
Yeah, so my name's Timothy, and I guess kind of similar to that question, I was wondering, as far as the number of harmonics that you'd get from the Fourier transform output, did you take all of them, or did you actually, I know you said you skipped a few, but would it have not been more relevant to have just taken the main harmonics and used those when plotting it and actually not using the lower magnitude harmonics, if that makes sense?
Yeah, so you can get, like, you can use all the harmonics, but it's also that thing of like, it's about time, right? But because what you do is to get the actual full size image, you're gonna divide 2 pi by the total number of epicycles that you have, right? Because the period of the entire Fourier transform is gonna be 2 pi. So the more you have in terms of like your epicycles, the longer it's actually gonna take. So that is the reason why so first of all, when reading the actual image, I don't read every pixel of it. And also when I'm doing pre-processing in that convert to phasor function within the Fourier transform itself, that's when I also remove more of them. So you can find that an image like this came down to like 4,000, 5,000-ish epicycles or harmonics instead of like, I don't know how many it started with. It was around 60 or something like that. So, but you still get a good enough image from that process. So, yeah.
Cool. Any online questions? Cool. If there's not any questions now, I know some of you are so brain, instability, but thank you so much. Ladies and gentlemen, Knowledge Dzumba.
Okay.